is Dr. Michael Mann. So I have to give a little bit of background about quantile regression first, because my comparison is actually between a simple linear regression and a simple quantile regression. So we have one X variable. So I guess starting off is, what do we use regression for in general? And I guess you could say businesses, schools, and individuals with particular needs, namely, statistical. They have, like, say, a bunch of observations, and they want to find trend in what they have at hand. And so we would say, mainly, that what we know is our data comes in, say, a pair. That means we believe there to be some predictable pattern or some, observable pattern that we can find in our data. Say if Y increases, X is likely to increase. That's the suspicion that we would have. And so there's various names. We can say X is the independent variable, or we could say explanatory. Likewise, we could say Y is the dependent, or Y is the response variable. And again, so we have to suspect that our data has some trend, and that's where we can actually use this. There's some other assumptions too, and I'll get to in a moment. So what we are trying to do is, we believe that our data comes from a population, and this is how we will notate that population. This is the standard stuff that you see. This is a constant. This is our coefficient, and this is our slope coefficient, and this is our X variable. This is all things that we've seen before, say in like algebra. What's new is that we have this error term, and this error term is variation in our model that we believe to be normally distributed, which would be, say, Gaussian, which is what follows a typical bell curve. So I'll cover some more assumptions on our error in a moment. But what we have in our, say if anyone is trying to run a regression, they're going to be likely running a regression on their sample data, nothing that relates to, it's suspected it's sampled from the true population. And that's a key idea here. And so we call an estimate, given that this is our population, our estimate of our sample, is of a similar form to our population. And of course, it's not likely that we're going to have the same constant or the same coefficient, but there's some, suspicions that they're going to be close, and likely, if we take a big enough sample, it will be very close. So just an illustration of some of the pattern. This is something that is like an archetype of what you believe to be, to follow a linear regression, which is simply just a straight line laid on a graph. So what we want to have here, when we're looking at our data to begin with, of course I say we suspect it, but what we have to look at is some things that make us suspect that we actually have a linear regression is appropriate. Namely, we want to look at the spread of our data, homoscedasticity. So this right here is that, at every point basically along this line, our data doesn't really vary too much from, say, this point to that point at any point. So that there's no really fanning out variation. That's not homoscedasticity, that's heteroscedasticity, and that's actually the problem we're going to cover later. There's no real outliers. The outliers just affect our graph, and so you'd have to have or be extra cautious in how you approach later on. But you might maybe say this is probably an outlier relative to this data being clustered really close to this tiny amount. Anyways, we can scrutinize more things later. So the simple linear regression is really just a trend line. It's the average of what we would expect our data to be along. This is our trend line. It's predicting the average among our data at all these particular x's, or these y's are the average given this particular x. And so this is an example of what it looks like. You don't see an error term over here because it's actually added to that because it itself is a constant. So this is a completely arbitrary example, by the way. I just put age and say money in your Roth IRA. So it's just something I thought would make sense. Also because as you get older, you likely have more money to put into your Roth IRA. That's what I figured would be right. And of course, I couldn't really remove this, but you can't really contribute to your Roth IRA until you're 18. But that's something I was hoping no one would notice. But I'll just be upfront about that. Yeah. So going back to the assumptions that we have, you can see that one of our assumptions, our first one, is that we believe it to be our data to be paired. That's really the main idea of all of this, is just we believe our data to come in a pair. And this extends to having more than just one variable, but we're just doing a single x variable. We have a completely random sample that's, there's no bias that we introduce, nothing, it's no way predetermined. Third is our error term, and I said earlier it follows a bell curve, so we just say it has a zero mean and a known variance. Again, this actually relates to the homoscedasticity, because if we have a predictable line, say going back here, say that we don't have an error term, and this is our line. That means we would believe it to follow straight on this line. But what we're saying here is that if our error has a known variance and it's fixed, then what we know is that it's really just going to be between, like, say, some specific pattern right here, and it's like this is the maximum variance given this line because we're just adding our variance up here, or say some amount, right? And of course you could have outliers. I'm not trying to say it's some fixed point that would be right above it, but it's just the idea. So then our fourth assumption is that we lack, this really only applies when we have more than one x variable, but we have no multicollinearity. That means we don't really have one variable predicting essentially the same thing. And an example I use is having a variable for gender and then say female, and obviously there's some aspect of gender captured by female. And so that's a kind of an example where there would be some multicollinearity there. And consequences of these, among all these things, is if we don't have, for example, if we have heteroscedasticity, then our error assumption is false, and that means we can't really use our OLS or simple linear regression as a model because it is flawed. And likewise for this one, if we have multicollinearity, then we just lose significance in our variable, and that's why just having one variable that captures, say, it'd be just a binary variable right here, but it is something that captures the idea once, whatever the idea is, being the labeled variable. So going forward, breaking our assumptions, like I said earlier, this right here is an example of homoscedasticity, that we just don't have too much, we don't have a fanning out variation of our data as it goes farther out on the x-axis. So I guess the problem here is that, or there is no real problem here, but the problem here is that if we did have heteroscedasticity, it would obviously have a fanning out effect, and I'll cover that in a moment. But this would be our third assumption, and like I said, this is a critical one. So, yeah, this is breaking our homoscedasticity assumption. And this is I keep mentioning the error term and why it's important, and the reason is because when we compare the quantile regression and the simple linear regression, I've just provided so much background on the simple linear regression that I haven't really mentioned the quantile regression. That's what I'm about to cover. But the quantile regression has, just to say, a better capability of predicting, say, percentiles of a distribution. So say this is the regression line, so it's the mean. If we're trying to predict, say, a line that goes out here, it's actually modeling not the mean, but say a different, say some percentile, say the 70th percentile. Well, given that the error term we're heteroscedastic, given that it fans out, we have a better capability of predicting and modeling with a quantile regression line versus a simple linear regression line, because our simple linear regression line has the assumption of homoscedasticity, whereas our quantile regression doesn't have that assumption, meaning it can handle the fanning out effect better. So I guess when I'm comparing my models, I kind of want to say, well, how is the simple linear regression worse or better, and by how much? That's really the main idea. And so these are just some ideas of simple linear. This is least squared regression, and this is, I guess, least absolute. This would be squared error, I believe. And this isn't supposed to say least squares regression. It's supposed to say squared difference, more or less. So we're going to say that if we have a model, I'm going to find actually what I have so you guys can see a good example. Yeah, right here. So this is kind of the idea. I didn't use the square difference. I used the absolute difference. So what we're having here is, say, this is the true distribution and the true line. Just simply true line, not true distribution. And this is the OLS line. So this is the mean or average approximation. This is the trend line that we find. And this is the quantile regression line at some specific tau being a percentile. So earlier I said 70, so you could imagine that we have some line that's predicting, instead of the mean, the 70th percentile. And again, this is a true line here that we're true line of our data. And so when we take the difference, we're saying that that's the error. That in how we want to determine which one's better is which one has a smaller error in sum. Meaning across the entire line, at every point along that line, our, say, estimated regression line or estimated simple linear regression line has a smaller sum, because that means it's truer and closer to the true line. So I'm going to go back quick. Yeah, so that's the idea of our loss function. I cover it later because that illustration I had is actually the loss function I used, but I didn't include a loss function here, but it's an important idea. So again, when we look at a quantile regression line or a simple linear regression line, we're trying, the value here in this, what I'm doing and what I've done is that we're looking at points, percentiles that are different. If we just look at the mean, then of course a simple linear regression is probably a better one, given if we have, say, a homoscedastic assumption. But it wouldn't be better for, say, a heteroscedastic assumption for our error term. Yeah, so like I said, what we miss out on, say, is perhaps the average, but we could, if we know what, say, percentile the average is at, we could find it with our quantile regression. But really, we're just trying to say that if we have a heteroscedastic error term, that we're able to use a quantile regression line to find that line better than if we were to, say, approximate that percentile with a simple linear regression line. And so I want to show you an example of what, earlier how this fans out, and this is our distribution. When I said our error term follows a normal distribution, say my drawn on normal curves are truly normal. Then as it fans out, our simple linear regression is not going to be as accurate modeling it, because as you can see, what would probably be the, say, 80th percentile right here is the 80th percentile here, here, and here, but it doesn't actually, we have more data points as we go out that are farther away from where we would be. So it's not an actual good way to model it with a simple linear regression. So again, we're not trying to find a trend line here with a quantile regression, or the trend line of the average. We're going to try to find some percentile trend line. And I guess there's no better or worse model in general. You kind of want to perhaps use both. I put down that they complement each other, meaning that in certain circumstances, it would be useful to know both. And because you can model different percentiles of a quantile regression, and there's really no loss if you use a quantile regression for a simple linear regression, depending on how you approximate your loss function. So here's actually a real-world example. So the father of quantile regression is named Roger Conker, and recently retired from UIUC. He is basically quantile regression, his brainchild, one of the gentlemen's, and here's an example that we have fanning out of our data, so it is heteroscedastic. This line right here represents our our 5th percentile. I believe that to be our 20th, and this dotted line is our median, and this thick blue line is our average, I believe, and then the top one is the 95th percentile, and I say 75th percentile. The next gray line down. So this is the idea that we value looking at these particular percentiles, because if we want to know, say, the household income of, say the household income is $4,000, and we want to look at we're trying to compare the difference between someone who's at the 5th percentile for how much they spend on food versus the 95th percentile, how much they would spend on food. You can't really see it in here, so maybe I should have said 2,000 because it looks a little better. But yeah, you just try to look at the difference in the gap between them. And what we believe is that given the error is heteroscedastic, the spread is larger, of course, between these two as the graph goes out. So it just captures the difference better. So my simulation, I was like this close to actually coming with photos so you guys could see something good, but I actually made a small mistake, and I've made mistakes all week, but the mistakes got fewer, but there weren't none in the end. So I was going to make a nice little box plot so you could see that the sum of every simulated model I did, all together, and then you'd see a nice box whisker plot. And so what it would be is that after, say, the 50th percentile, the sum, both boxes, error sum is going to go up. But there's going to be a bigger spread for heteroscedastic data. There's going to be a bigger spread on our simple linear regression for heteroscedastic data. That would mean that it just is worse at modeling heteroscedastic data, and that would have been really nice, but I don't have it. And even in my work that I don't have to show you guys too, is this was, like I said earlier, my loss function. And again, we want to lower sum for whatever one we're going to compare them to. So if we have a simple linear regression line, we want it to have a lower sum of error if we're, say, going for the mean against, say, whatever other thing we're going to model anyways. That's really it. And I only really use one source. And I use Wikipedia here, but that's for an image. And as you guys can see, when I was actually saying the columns of those, one of them was wrong. So Wikipedia can be wrong. I believe I might be wrong even saying it's wrong. I don't know. So yeah, I'd like to thank the McNair program for funding me through my undergraduate. It's been really great, and it's not so much worrying about like 20-hour work weeks. And then definitely for Dr. Minotti, because I couldn't be doing what I wanted to do with the McNair program unless someone took me under their wing, and Dr. Minotti has. So, and I got accepted to grad school too. I got accepted to Carnegie Mellon's PhD program in economics. So I am moving on, and that's.
Ask if anyone has any questions.
Oh yeah, any questions? Yeah, I think that's the next slide.
So before this quantile regression method was developed, were there problems that just couldn't be analyzed very effectively, or?
I actually don't know the answer to that question. I would say that there was probably just a greater improvement to the accuracy of predicting percentiles with heteroscedastic data. That's really all I can say.
I was just going to say thank you for your presentation. You have a very bright future, I think, in mathematics. You explain things extremely well. Very understandable.
Thomas, what would some real-world examples be like for business, industry? I mean, from what you've explained, some things come to mind, and I just was wondering,
Yeah, so I used the example of that Confer used in his book, this book. I believe that's a book. No, that's an article. But anyways, yeah, so this is an example. So it's really just, you kind of would suspect these kind of, you suspect this. Okay, so imagine as household income increases, it's not necessarily true that you would spend more money on food. It really kind of, you'd also think it depends on how many people are in your household. And that's not something that's captured here, unless it was conditional. They modeled that. But another good example is actually on earnings, because it's not necessarily true, or earnings in education. It's not necessarily true that as you're in school longer, that you'll earn more money. That's not necessarily a true thing. And so that you would see some fanning out effect in that data as well. And I can't really think of anything else on the top of my head.
but where to develop certain, certain industries or where to locate certain businesses based on, the higher end, where they spend more on food.
Oh yeah, that's
To me, it would be very relevant.
Yeah, I guess you could say. Well, I guess I'm not sure if this would have any actual oomph in predicting something where people would spend, because that doesn't really go with what I'm modeling here, at least to my knowledge. But yeah, I guess if you put stores in neighborhoods that are more affluent, then I guess that's the kind of an example.